Okay, so welcome to the final lab of the semester, and we will be learning and reviewing a little bit about earthquakes, and you'll be doing some exercises based on movement around faults or plate boundaries, how you find the epicenters of earthquakes or the location above ground that's located above where the earthquake actually occurs, and the timing of earthquakes. So this is the last lab we'll be doing, and it is due next week on Monday, April 26th at 11:59 p.m., along with the Lab 8 Metamorphic Rocks quiz, because as Jorge was kind enough to point out, it had not been converted to an online format yet, and Dr. Bird and I just got that done. So next week, I will be hosting a class session at the usual time at 11 o'clock. It will not be a formal lab, though. I will record it. I'll be doing a brief presentation on what kind of material you can expect on the final exam, and I'll be putting out a study guide with key terms and things to study prior to that. The final exam is going to open next Tuesday on April 27th, and it's going to be open until Friday, May 7th at 11:59 p.m. Friday, May 7th is the last day of the semester, so that's the hard deadline for submitting any work. If there's any labs or quizzes you have not done yet, I am not going to penalize you for lateness at this point, because I recognize everyone has a lot going on, and the format of this class makes it a little easier to do that. But you need to get it to me before May 7th, because after that, I'm going to have to start compiling grades. I will have a little more on the exam format next week, but it's going to consist of 46 multiple choice questions, each of which are going to be 2 points. So there aren't going to be any free response questions like you have on the lab sometimes. And the questions will be similar to the quiz questions. They'll be based on maps and pictures or videos of minerals. I also wanted to mention that there's another extra credit opportunity for those of you who might be looking to get some extra points for your quizzes, especially. And Mariana, I'll go ahead and let you ask your question first before I get into that. I'm listening.
Thank you. I just wanted to know, have you put in the extra credit for the last?
Thank you. I have not put in your points just yet.
Okay, that's totally fine.
I was going to message you with that.
All right, thank you. And I had another part of the question. For this extra credit opportunity, are we going to be turning it in as you had the last one, just emailing it to you?
Yes.
Okay.
If you attend
Oh yes. You also have the USG seminar extra credit, and that's due like as an upload window on Canvas, correct?
Yeah, I need to actually look at if that's doable, because that was actually something that just came into the course when I imported it from when it was taught in fall 2020. So I can check that for you to see if that's still doable. I actually earlier this morning hid that because I was looking through the different assignments and realized that might be something that's not doable anymore because the seminars might have happened last fall and might not be available, but I will look to see if there is anything you can do with that.
Thank you.
You're welcome. So yes, as Mariana mentioned, I'm looking for about a 1-page, 400 words-ish write-up on what you learned at the talk, and it's pretty open-ended as to what you write about. We have a research scientist from the Geological Survey in Illinois giving a presentation. So it'll be happening next week, April 27th, after our class meets from 5 to 6 p.m. And each extra credit assignment adds 3 points to, I can add those points to a quiz or to a lab. And I mentioned that I will be curving some of the quizzes upward. I will let you know exactly what I'm doing with that and when I add the extra credit points. I might curve the quizzes and then add the extra credit points to a lab. But if you submit one of these assignments and you have a strong feeling about what assignment you'd like the points to be assigned to, you can shoot me an email. Any other questions? And I'll shoot an email once I get a study guide posted. Okay, cool. So today we'll be talking about earthquakes, and earthquakes are mostly about plate movement. And the plates aren't really sliding past each other neatly. There is a lot of friction involved, especially at convergent plate boundaries where you either have subduction or where you have plates colliding and building mountains. And earthquakes occur as a result of stress building up and being released. And on this map, this is a map of earthquakes that have been moment magnitude scale 5.0 or higher from the past decade. And most of them correspond with plate boundaries, but not every single one of them. You can see that there are scattered dots. For example, there's a bunch in the Australian plate out in the middle of the ocean. There are a few in Eastern North America, even though Eastern North America is actually nowhere near a plate boundary. The plate boundary is out in the Atlantic Ocean. You might notice that the biggest clusters of earthquakes occur in places where we have subduction or mountain building. We have a lot of earthquakes along where the Himalaya are, where the Indian plate and the Eurasian plate are colliding. We have a ton of them off the west coast of South America, where the Nazca plate is subducting under the South American plate. And we don't have as many earthquakes at the spreading centers. We have some, but it's not quite as thick of a band of orange dots. Why might we have more strong earthquakes at subduction zones and mountain building areas than at spreading centers? What's different about the crust at a spreading center versus where it's subducting? Which one is cooler, temperature-wise?
When they are spreading.
It's actually the other way around, because when they're spreading, they have very recently been magma. The rocks right at the spreading, the ocean crust right at the spreading center is going to be very young and relatively warm. And the key part related to that is that when the rock is warmer, it is less brittle. It's able to handle stress better. So at the subduction zones, the downgoing oceanic crust is colder and creates more friction with the overlying plate. Not to mention that at continental collisions, where you have two continental plates, continental crust is just thicker in general, and you get very large earthquakes when you have faults on continental crust. So that's why spreading centers don't tend to have divergent plate boundaries. Spreading centers don't tend to have as big earthquakes because the crust there is relatively warm and relatively young. Does that make sense? Now, oh, sorry, yes?
I was just going to say yes.
Okay, cool, glad to hear that. So as for transform boundaries, it depends on whether they are cutting through oceanic crust or continental crust, because most transform faults occur as the connector segments along the mid-ocean ridge. Like you'll have the spreading center segment, and then it'll be staggered with a transform fault, and then there'll be another spreading center segment. Those don't tend to produce huge earthquakes because they're cutting through young oceanic crust, but the one example that's clearly visible here, the San Andreas fault, is a rare example of a transform fault cutting through thick continental crust. And as we all know, we get significant earthquakes in the fault zone of the San Andreas fault. And when I say fault zone, I mean that there's actually a lot of faults that run more or less parallel to the San Andreas fault that a lot of earthquakes occur along also. The Ridgecrest earthquake a couple of years ago was along one of the subsidiary faults that was running parallel to the main San Andreas fault in the fault zone. It's caused by related tectonic processes, but the movement didn't occur directly along the big fault itself. So any questions yet? Now, an earthquake is more or less just when the Earth moves in response to stress. And it is usually caused when stress builds up along a plate boundary. And a plate boundary and a fault are not quite interchangeable because you get little faults that run parallel to the main fault that defines the plate boundary, but I'm kind of using them interchangeably just for the sake of simplicity a little bit. You can get earthquakes when you have volcanic eruptions, and that means you sometimes get earthquakes at hotspots when you have, say, one way they can detect an imminent volcanic eruption is from the movement of the Earth, because that is often associated with magma filling the magma chamber underneath the volcano before it starts to erupt. Of course, a lot of volcanoes do occur right at plate boundaries, but sometimes you get earthquakes at plate boundaries that have more to do with magma chambers filling than movement along the fault itself. And then again, sometimes you have hotspots, which are volcanoes that occur quite a ways away from plate boundaries, and you can have earthquakes there from magma moving around under the ground. Fracking can also cause earthquakes because it generates a large enough force to do that, and it also involves it involves removal of large amounts of material, and that can cause collapse. Atomic explosions also generate enough force to cause earthquakes. I'm joking a little bit with the dinosaurs, but hypothetically, you could get an earthquake from a large enough herd of dinosaurs. Earthquakes aren't only caused by fault movement, but they are mostly related to plate tectonics. And the idea is that the Earth and anything else damaged by an earthquake gets briefly distorted as stress builds up. Up until a point, solid objects will bend rather than break. And solid objects have an easier time bending or deforming in response to stress, as opposed to breaking apart in response to stress. It's easier for them to deform if they're warm, which is again why you get less strong earthquakes at mid-ocean ridges where the crust is warmer than you do at subduction zones where the crust is colder. So the Earth and whatever is alongside of it deforms. And then the rupturing, the actual earthquake itself, happens when the energy builds up so much that the Earth can't really resist that anymore. It breaks and forms a crack. And when the earthquake releases, the rocks will rebound to their original shape more or less, but they will have shifted position. As you can see in this case, where the bit of a human structure built across this fault, this fence, shows displacement now. And what type of fault is this? What type of plate boundary would this be associated with? Does this look like a convergent, divergent, or transform fault to you?
The divergent?
That's a good guess because it does involve stuff coming apart. Divergent and convergent both involve up or down movement, though. Divergent usually involves dropping, and convergent involves stuff going up. Is there any up or down movement occurring here? Like, is the level of the ground changing?
Not really.
Not really, precisely. There's no up or down movement, but there is side-to-side movement. So this is a transform fault, actually. And it is worth noting that most transform faults do experience at least a little bit of up or down movement. It's very rarely absolutely 100% only sliding horizontal movement, but it is most heavily dominated by that. And I'll have a little bit more on that on a couple of slides. I just wanted to throw that out there. And at a given fault or at a given segment of a fault, because we have to break large faults like the San Andreas Fault into segments to study them, stress builds up periodically at a pretty regular rate. There's what's known as a recurrence interval, which is the amount of time that passes, whether it's 20 years, hopefully not, or 500 years, or 1,000 years. It's the amount of time between two large earthquakes, and a large earthquake is sort of arbitrarily defined as an earthquake that's motion magnitude scale 7 or higher. And in general, faults are going to experience a lot of little earthquakes all the time because little movements occur in response to stress. But little earthquakes don't really release the stress that well. And so over time, the stress will build up as the tectonic forces deform the rocks on either side of a fault. And eventually the rocks will fail. The stress will build up enough that the rocks simply break, and you'll have the fault slip, releasing the stress and releasing that stress as energy that is felt as the earthquake waves and causing an earthquake that destroys human structures and has the potential to hurt people. And what the recurrence interval is going to depend on what type of tectonic setting we're dealing with and what type of rock they're cutting through, because different rocks have different amounts of strength. And so some types of rock are going to, for example, thicker. So if the rock is thicker or older, it's going to probably have a longer recurrence interval. And it's going to also produce dramatic earthquakes at that recurrence interval. And that's the situation with the San Andreas fault. So a fault is any place in Earth's crust where the crust moves. When I say opposite direction, I mean in different directions, like whether like one side is moving up and the other moves down, or one side moves down and the other moves up or kind of stays in the same place, or where they slide past each other in different directions. All of those cracks where that type of movement occurs are examples of different types of faults. And along a plate boundary, you do usually have a fault that defines the plate boundary. You will also have a series of faults that run parallel to that main fault and are caused by the same processes that cause the main fault, but they don't exactly correspond with the plate boundary itself. For example, the plate boundary between the North American plate and the Pacific plate is defined by the San Andreas fault. The San Andreas fault has a number of faults running parallel to it, like the one that caused the ridge crest earthquake, as well as the Hayward fault, which is a transform fault caused by the forces that cause the San Andreas fault that is a bit offset from it, and that also happens to run right through the UC Berkeley Stadium. And though there hasn't been a dramatic earthquake along the Hayward fault in a while, you can still actually look in the stadium and see how there's been little bits of offset, how there's been a little bit of structural damage from the plates moving side to side. And the fault that I had the example of before, as well as the San Andreas and the Hayward fault, are known as strike-slip faults because the movement occurs horizontally with little to no vertical movement. We didn't really talk much about strike and dip in this class, but the strike of a geologic feature is basically what compass direction it's cutting in, and strike-slip faults are known as such because they move along the strike of the fault. Faults that occur at convergent and divergent plate boundaries, which we'll talk about next, are known as dip-slip faults because they move either up or down. And the dip of a fault is kind of sort of what angle it's at. You don't have to worry too much about strike and dip, but that is something that you will come across if you take more advanced geology classes and start doing any field work. And strike-slip faults can be found. They can be found at different. They can be found at different tectonic settings, but they're found along transform boundaries. They're found at the San Andreas faults and the surrounding faults, as well as in the connector segments that we have in mid-ocean ridges. And they will often cause distortion like this, where it just looks like somebody took part of the fence and just shoved it over to the right a little bit. It wasn't a person who did that, it was the earth underneath that's moving, because in California especially, we have a lot of places where farmers or people built fences or houses over faults without realizing where the faults were. And we have a lot of historical pictures of their property being whooped by lateral or sideways movement along the fault. So any questions? One thing I want to mention is that, and I have this little animation here, this is what I mean when I say that mid-ocean ridges have transform faults. Mid-ocean ridges have these divergent plate boundary segments where crust is separating in either direction, and they're connected by transform faults. The interesting thing is that you have these dead faults as you move away from the mid-ocean ridge. This is not a plate boundary here. The plate boundary is defined by these divergent segments and then the transform segments that connect them. Out here, there is a crack, and that's left over from the fault, but the crust on the upper side of this crack is moving to the left, and the crust on the lower side of this crack is also moving to the left. And the reason this exists is because the transform fault segments that connect mid-ocean ridges will actually change size over time. They will get wider or less wide over time, and hypothetically, this fracture zone could be reactivated. Part of it could be reactivated as part of a transform fault, but it's not being used presently. That's not really something that comes up in this lab, but I think it's an interesting, in terms of just studying plate tectonics in general, it's something I just wanted to mention. Now, one thing to consider is actually you can define transform faults by whether they are left lateral or right lateral. And the terms left and right always refer to one's viewpoint. They aren't fixed like compass directions. You have to define to whose right we're talking about. So on a strike slip fault at a transform boundary, picture that you're on one side of a fault boundary and that you have a friend on the other side of the fault boundary. In this diagram, on the lower left corner, the fault is a right lateral fault because if you are in the red car, from your perspective, your friend in the blue car is going to move to the right. Now, even though you are moving to your left, from the perspective of the person in the blue car, you are moving to their right. If you're in the blue car and facing directly at the fault, you're going in this way, and that, from their perspective, is to the right. Meanwhile, at a left lateral fault, it's the opposite situation. At this left lateral fault, if you are on the lower side of the crack here and you're looking directly towards the fault, movement occurs like such, and you are watching your friend be moved to the left from your viewpoint. The San Andreas fault is a right lateral transform fault because the Pacific plate, which a lot of California is located, a lot of coastal California is actually technically located on the Pacific plate, that is moving north, and the North American plate is moving south. So if you were to speed up time and you were standing on a mountain in the Coast Ranges and watching the land move, you would see Los Angeles and Fresno move south, move to the right relative to you, and you would be moving north. So from the perspective of someone in Fresno or Los Angeles, you would also be moving to the right. And here's another example showing how distortion can happen from transform faults. This is an example of where you have a stream that used to flow continuously, and then movement along the San Andreas fault, the right lateral San Andreas fault, caused a shift. And so now where the river comes out of these hills is offset to the right of where it was originally. So any questions about transform faults? So transform faults are also known as strike slip faults. Strike slip faults are defined as opposed to dip slip faults. And dip slip faults are faults in which movement occurs vertically primarily. And if you have one block dropping down, you have this occurring as a result of extension. This is usually something you find at divergent plate boundaries. If one of the sides moves up, that is going to be from compression. And the way to figure out whether something is going up or down, whether it's a reverse fault that goes where one side goes up or a normal fault where one side goes down, is to look at what is known as the hanging wall. And the hanging wall and the footwall are terms that we do not really use these for strike slip faults because, again, that movement just occurs horizontally. Dip slip faults are going to be at an angle usually. They're usually very steep for faults that involve dropping, and a bit less steep for faults that involve compression and rising. But we have this cross section here, and we have a dip slip fault that is cutting through the earth. Oops, sorry about that. Now, if this was like a block model, you could imagine sort of taking away the left side of this block model. It's like a piece of a model that you can physically move up and down with your hands. If you physically take this away, it's going to make a shape where there's this point hanging off. It kind of looks like the Jawa sandcrawler from Star Wars, in my opinion. But this is the hanging wall, because if you were to separate this block, you could, like, if you just separated this and like had it by itself as a cliff, you could hang something from it. In this diagram, I like this diagram because it shows sort of how you could envision this if you were still underground. So you have a fault along which an ore vein is cutting into, and you can hang a lantern from the hanging wall. The footwall is the other wall. I actually find that the footwall, in sort of a crude, broad way, resembles like a kid's drawing of a shoe, sort of. So that's how I remember which side of a dip slip fault is the footwall. The hanging wall looks kind of like a Jawa sandcrawler, or it has the point that you could hang something off of. The footwall looks like a shoe. And the terms footwall and hanging wall by themselves don't say anything about which way the fault moves. You have to use the displacement that occurs to observe which way it has moved. So in this diagram here, you can see actually that they've colored a bunch of layers of sedimentary rocks differently. You'll notice 2 consecutive brown layers here. And the only other place you have 2 consecutive brown layers on the other side of the fault is up here. So you'll also notice that the ledge is sort of sticking up here. Has the hanging wall moved up relative to the footwall or down relative to the footwall?
Up.
Yes, it's moved up. So this is what is known as a reverse fault resulting from compression. And it's honestly kind of arbitrary which one is normal and which one is reverse. Normal faults are faults where the hanging wall moves down, and those are associated with extension. When you have the crust coming apart and the block just sort of drops down. And this is a feature that we see in places like Death Valley, where actually in an ocean you were getting oceanic crust, and you were getting a rift valley that never got wide enough, that never extended far enough north or south to let ocean water in. But normally normal faults will usually actually be really steep, because the hanging wall drops down pretty rapidly. Reverse faults occur when the hanging wall moves up as a result of compression, and you get reverse faults at convergent plate boundaries, and they will usually have a much shallower dip, because when you have a convergent plate boundary, you'll have the rocks usually distorting and folding a fair bit before you actually get breakage and movement. And this picture shows what's called a drag fold, that shows that the layers of sedimentary rock got folded, they got distorted a little bit, and then moved like this. So that's not really something we linger on in this lab much, but it's pretty cool to think that there's these complexities to fault movement, that sometimes that you can see evidence of the rocks being distorted before they gave way to the stress and simply ruptured. And I mentioned Death Valley before. Death Valley is a really good example of what's known as Horst and Graben topography, when you have you have sort of opposite facing normal faults on either side of a valley. You have this block in the center that drops down, and you have normal faults on either side of it. You can see how the block underlying this valley, the layers in this valley are dropped down both relative to those on the left and relative to those on the right. And this will often occur in a broad area that is experiencing extension. This has occurred in the Great Basin, or excuse me, in the interior of the United States, where you have frequently these long mountain chains, and then a long low valley, and then a long mountain chain on either side of it, and then another low valley, and that's what's known as basin and range. So Horst and Graben is another way to say basin and range, but it's a result of normal faulting. You also get normal faults at mid-ocean ridges, where the crust is being pulled apart. And I mentioned Death Valley being a rift valley. A rift valley is a valley formed as a result of normal faults, as a result of divergence. And it is is an incipient mid-ocean ridge because you have some volcanoes occurring here. The volcanoes along the Great Rift Valley in Africa are they are caused by divergence, and eventually you will get an ocean here as the valley drops down low enough that water from the Indian Ocean and the Red Sea will flood in. Now, reverse faults you often find with mountain building. Reverse faults, literally, a lot of mountains form simply from the accumulated effects of upward movement along reverse faults. And this is essentially how the Himalayas were uplifted. The Himalayas were uplifted by lots of little movements along reverse faults. It is still occurring to this day. We don't really observe it happening because the movement is even when you have a large earthquake, the amount of movement along the fault is going to be pretty small. The earthquakes that caused, for example, there was a big earthquake in Nepal about 5 years ago in Kathmandu that destroyed a lot of the city, and that was an earthquake related to movement along a reverse fault. When you had upward movement of the hanging wall and you had thick continental crust on either side of the fault, that generated a lot of friction and caused it to build up for a long time before the stress was released and before movement occurred. It was still relatively little movement along the fault, but even that still released a lot of energy. And over geologic time, the accumulated movement along these faults lifts mountains up. So you also get reverse faults at subduction zones. At subduction zones where one plate is going under the other, you'll have a pile of sediments forming that are sort of trapped between the downgoing oceanic plate and the overlying continental plate. This happens most frequently. This usually happens where you have ocean going under continent. And the sediments in what is known as the accretionary prism, named for its shape and by the fact that the sediments are sort of being accreted or pushed towards the land, you get a lot of little reverse faults forming there. A lot of little faults where there's upward movement. And remember that plate boundaries are usually defined by a cluster of faults that have the same trend. So we can see places where, like along the San Andreas Fault, where there's a bunch of little faults roughly running in the same direction. So any questions about different types of faults, like normal versus reverse, strike slip versus dip slip? Transform boundaries equal strike slip faults. Divergent plate boundaries equal normal faults where the hanging wall moves down. And convergent boundaries cause reverse faults where the hanging wall moves up. So then let's talk a little bit more about earthquakes themselves and how they manifest. So the hypocenter, or the focus of an earthquake, is going to be where the rupture is actually occurring inside the earth along the fault. And this is important to consider. For a lot of earthquakes, the hypocenter is not the hypocenter is very likely not going to be right at the surface. The actual oops, that is my cat walking on the keyboard. Maki, get off the keyboard. Maki, get off the keyboard. Okay. Okay, she muted me, but hopefully, okay. I do not believe the computer is muted anymore. I apologize for that. Meanwhile, the hypocenter is underground, usually along the fault where it is actually occurring. Now, you will more frequently hear about the epicenter in the news because the epicenter is the location on the surface directly above where the hypocenter of the earthquake is. And is epicenter A in this diagram directly along the fault itself? Oops, sorry about that. So the question was, is the epicenter is the epicenter located exactly where the fault is? Or is it a little bit offset from the fault?
Right on it.
Offset.
It is actually just a little bit offset. The hypocenter is right along the fault, but if you notice, if you go directly up, you're no longer along the fault itself. Where the fault actually manifests at the surface is over here. So the epicenter is actually just a bit offset from where the fault actually is manifesting above ground. Because you'll notice this, like most, you'll notice this is a dip slip fault. This is a normal fault where the hanging wall has dropped down, and it's at an angle. So if you go vertically directly above where the hypocenter is, you're no longer going to be on the fault itself. Now, with strike slip faults, since you usually have a more or less vertical fault, this is going to be less of an issue. And I say issue in terms of locating the earthquake and figuring out where the fault is itself. For strike slip faults, since they're more vertical, the epicenter is usually going to be still on the fault itself, but not always precisely. So the hypocenter or focus is where the actual rupture occurs along the fault. The epicenter is directly above that on the ground. So that's why, for example, the Northridge earthquake, the epicenter was in Northridge, Los Angeles, and the hypocenter was close by, but the location that they gave when referring to the earthquake is the epicenter, or where the earthquake is centered above ground, and not where it actually ruptured underground. So again, what happens at a fault is that stress builds up and you get small amounts of elastic deformation. You can see that in this, here what's happening is that the rocks are changing shape a little bit without completely breaking. And then you start getting cracks, and eventually the cracks coalesce or go from being a bunch of little cracks into one big crack. They fail and the rupture releases energy. And especially, again, if you have very thick crust or very old crust that is very cool and dense, when the movement happens along the fault, it's going to create a lot of friction. That's what causes the actual feeling of the earth moving around a lot. Also, the fact that if the crust is colder, that means that it deforms less effectively in response to stress, and the stress will build up a long time and be released kind of in a gigantic burst. The interesting thing is that this diagram sort of shows how new faults can develop. Faults are not permanent features that have necessarily always been there. New faults form all the time, and one thing that frequently happens is that old movement along old faults will be deactivated. You can sometimes have faults that formed from a geologic process millions of years ago. It's possible, if those faults still exist, for them to be reactivated by other geologic processes millions of years later. And I'll actually talk a little bit about how some of the earthquakes that occur in the middle of plate boundaries can sometimes be caused by movement along ancient or dead faults. Now, we measure earthquakes by using a seismometer, actually almost always by using a pair of seismometers, because we need one seismometer to measure vertical movement, like to measure whether the ground is moving up and down, and then one for horizontal movement to see to what degree the earth is moving from side to side. And the classic model is to use the one like Stan's dad from South Park is using here, where you just have a pencil that's sort of scribbling. A lot of these are electronic now, though. A lot of them generate an electronic signal instead. It's still very useful to have the pen rolling on paper ones sometimes, because they are a bit easier to maintain, and they're sometimes very useful for remote or difficult to reach stations, especially ones where they can't easily establish an internet connection. Now, is Stan's dad getting all the information he needs about the earthquake from just this one seismometer? Are you getting all the information you need from just one seismometer, or do you need more than one?
More than one?
Yes, you need more than one. You need one to measure vertical movement and one to measure horizontal movement, and this one is really only measuring horizontal movement. So easier to animate, but not completely accurate as to what scientists use. I've alluded to earthquake magnitude before, and there's actually several different scales by which scientists measure magnitude, the same way that there are different scales that scientists use to measure temperature. You have degrees Fahrenheit, degrees Celsius, and then degrees Kelvin, which are based on the Celsius system, but defined relative to absolute zero. Earthquake magnitude is always pretty much measured proportionally to ground movement or area of or the area that's ruptured. So the amount by which the ground is moving or the area that's being ruptured. And all of them are logarithmic. Oops, cat on keyboard. She wants attention today. An increase from 1 to 2 on the scale doesn't mean that you have twice as much of the movement. It means you have 10 times as much the movement. You're going from 10 to the first power to 10 to the second power. And the energy actually increases even more quickly. The energy increases by a scale of 32. So this is why the earthquake scale numbers aren't that big. Like you have a 7 earthquake being considered big, but that has 10 to the 7th times as much. That means that the fault there is 10 to the 7th power times as much movement along the fault as there was if it was a 0 scale earthquake or very close to 0, because you can have less than 1. You can have earthquakes that are 1.5. You can have earthquakes that are 0.5. But that's basically what the earthquake scale measurements are based on. Not something you need to deal with that much directly for this lab, but that's how they are defined. Earthquakes often occur in clusters. You'll often have a large earthquake that is accompanied by foreshocks, or these small earthquakes that occur before the largest earthquake, and aftershocks that occur after the largest earthquake. I meant to put largest here. That's a typo. Now, is it possible to figure out which one is the foreshock before the whole sequence of earthquakes is done? If foreshocks are defined relative to which is the largest earthquake, can you know what the largest earthquake is before the whole sequence is done?
No.
Nope, we can't really predict foreshocks. If we get an earthquake, it might just be a small earthquake, or it might be a foreshock that precedes a larger earthquake, and that's a little scary in a way. Aftershocks, we can figure out what they are almost immediately because we will have had a large earthquake, and then the smaller earthquakes that occur afterwards are technically considered aftershocks. And aftershocks occur because you have sometimes not all of the energy is released at once, and that's fundamentally also why foreshocks occur. You'll have a little bit of movement, kind of like the fault beginning to slip, and then you'll have the big slip, and then you'll have a little bit movement afterwards as the last of the energy is released. You might also have aftershocks occurring along the faults that run parallel to the big fault in the fault zone. And earthquakes involve energy. Earthquakes involve the energy being released from the hypocenter or focus, and energy travels in waves. Waves, like ocean waves, don't actually involve the movement of material for the most part. There is a little bit of movement of material due to friction, but in this example, this seagull is just more or less bobbing up in the same place. And you'll notice that the seagull gets moved up and down a little bit, but it doesn't actually get carried by the wave. The wave is moving energy, and the actual water molecules aren't really moving. It's just the energy is rolling through the substance they're rolling through, aka the water. And as you can probably guess, energy passing through a brittle substance is going to cause a lot more damage than a wave simply passing through a fluid. In the case of earthquakes, we have body waves, which refer to how the energy behaves when moving through the earth, and then surface waves, which occur when the energy reaches the surface. For this lab, we'll only really be focusing on two types of body waves, which are P waves and S waves. And P waves are primary waves, and they're the first to show up. And the particles disturbed by energy in P waves move parallel to the direction that the energy is moving. If the energy is moving this way, that means that the movement is occurring parallel to that to the left or right, kind of like a slinky going in and out. Whereas S waves, secondary or shear waves, involve, if the energy is going this way, the shear waves are going up and down. They're going perpendicular to the main axis of wave propagation. And the key thing about S waves is that since they involve shearing perpendicular to the direction of movement, they cannot travel through liquids because liquids cannot be sheared. So to show you what I mean, a slinky being pulled in and out actually involves a type of wave. It involves energy being moved around. The slinky is being pulled left and right, and the wave is propagating to the right. That is parallel to the direction of the particle movement. And you can kind of see that occurring with the animation here. You can see this black dot is shown. It's not shown moving up and down at all. It's just shown moving back and forth. And this is how primary earthquake waves behave. And primary waves can travel through both liquids and solids. Meanwhile, S waves can only travel through solids. And this is what I mean when I say that the particle motion occurs perpendicular to the direction in which the wave is propagating. In this example, the wave is still moving from left to right, but the particles that are disturbed are moving up and down. And so with earthquakes, P waves will travel through the entirety of the Earth. They will be able to pass both through the solid layers of the Earth, like the crust, the mantle, and the solid inner core. And they will also be able to pass through the outer core of the Earth. And the outer core of the Earth is liquid. The outer core of the Earth is made of mostly of molten iron and nickel. And fun fact, it's actually what is generating Earth's magnetic field. The reason Mars doesn't have much of a magnetic field anymore is because its core has become completely solid. Now, you'll notice that when the waves pass through, they are being bent. And that's because you have a different chemical composition of the mantle compared to the chemical composition of the core, compared to the chemical composition of the crust. That causes the waves to travel at different speeds and to be refracted when they pass from the boundary from one layer to the next. And one method that scientists have actually used to study what is inside the Earth is to look at the movement of P and S waves. Now, the fact that scientists were even able to determine that the outer core of the Earth was liquid was that they were able to realize that the S waves produced by an earthquake on this side of the Earth simply didn't travel to the other side of the Earth. If they hit the outer core, they simply stopped because the energy couldn't travel through the outer core. So earthquake waves are actually one big tool that we have to study the interior of the Earth, because we don't know much about the interior of the Earth, really, and we can't go down there because the pressure and temperature will do to our bodies what they do to metamorphic rocks, which we will not survive. So earthquake waves help us study the interior of the Earth a bit more safely. I just have a few more slides after this, but any questions? So I alluded to before that you get different scales of earthquakes at different tectonic settings. You can also get earthquakes inside plate boundaries. At divergent plate boundaries, you have crust that is warm and young, and you get a lot of small earthquakes at divergent plate boundaries. The stress is released more or less continuously, and you don't get big catastrophic earthquakes. big catastrophic earthquakes tend to occur more at convergent plate boundaries, at subduction zones, and especially at collision zones. And this involves older oceanic crust crushing against thick continental crust, and even you still get big earthquakes even when it's an ocean plate. Japan has plenty of big earthquakes, even though that's an example of ocean crust going under ocean crust, because both of the oceanic plates are relatively cool. They're not anywhere near as warm and thus as ductile and plastic as they would be if the crust was still right near the spreading center itself. So it's not a coincidence that a lot of the places that are known for really destructive earthquakes are located at convergent plate boundaries, like along subduction zones especially. You can see there's this trench off the coast where you have subduction occurring off the coast of Japan, and Japan has had plenty of big earthquakes. Alaska is another good example. And the earthquakes in Alaska are largely from subduction along the Aleutian Trench. You have the Pacific plate subducting underneath. I think this is part of the North American plate still. I actually need to look exactly where that is. But this is also ocean. You have some oceanic crust here. And you get a chain of volcanoes, the Aleutian Islands forming, and you get many big earthquakes. And you don't get nearly as much property destruction because you don't have as many large cities, but this picture is actually from a tsunami or a gigantic wave that was produced by fault movement. Tsunamis are caused by movement along the seafloor, where a underwater fault, often case where you have a reverse or convergent plate boundary fault moving slightly upward, and that displaces water upward and creates a wave that gets pretty darn big. So it's kind of strange to think that those gigantic waves that destroy property and kill so many people are just caused by a little upward movement on the seafloor, but that water displacement causes a lot of damage. And you get really violent earthquakes where you have continental collision occurring. This is occurring in slow motion, but again, you have the force of one massive continent slamming into another massive continent, and that builds up a lot of pressure, and when the pressure builds up, it comes out as a very violent earthquake. So this is the earthquake in Nepal that I was referring to before. This is a really horrifying example of an earthquake at a continent convergent plate boundary where you have continental collision going on. Oh, that was a cat. Something I wanted to mention that relates to the fact that earthquakes are going to be stronger when the crust is cold or brittle is that at subduction zones, you only have earthquakes above a certain area. The term the Wadati-Benioff zone, which isn't something you really need to memorize for this class, but it refers to the zone above which earthquakes can occur. As the downgoing plate gets farther down, it's going to get warmer, and thus you're going to have less friction. So earthquakes occur along the fault in the Wadati-Benioff zone and the zone above where it's too hot. The Wadati-Benioff zone is where it's cool enough for energy to build up and for earthquakes to occur. And remember that earthquakes occur along the fault itself. The hypocenter is going to be anywhere along here. If an earthquake occurred here and the hypocenter was here, as you can see in my cursor, the epicenter would be directly vertically above, and the epicenter wouldn't necessarily be right along the plate boundary itself. Often we don't feel all the deeper earthquakes because the energy doesn't necessarily reach the top that strongly. Sometimes smaller earthquakes are caused by deeper earthquakes. And most transform boundaries don't have particularly strong earthquakes because transform boundaries usually occur as the connector segments along mid-ocean bridges, where they're cutting through young, thin, and warm, and thus pretty plasticky oceanic crust. But we have one weird situation where a transform boundary is cutting through continental crust on both sides, and that generates enormous earthquakes. And so the San Andreas Fault is really quite unique in that way. It is actually technically connecting two mid-ocean bridge segments. There's ocean spreading going on in the Gulf of California, and there's ocean spreading occurring off the coast of California and Oregon in the East Pacific Rise, but there's a very, very long connector segment between them that happens to cut through land. And the study as to how the San Andreas Fault got to be the way it is still ongoing and still a pretty complex story. One part of it is that the reason the San Andreas Fault makes the big bend it does around where I live in Santa Barbara is that it is literally making a turn around some very thick old crust in the Mojave Desert that it doesn't have the energy to break through. And not to anthropomorphize faults much, but they will tend to break where it's easiest. Intraplate earthquakes are a weird situation where you sometimes have hotspots involved. A massive earthquake in the small town of New Madrid, Missouri, which is down in this little part of the state, what's known as the Missouri Boot Heel, that is nowhere near a plate boundary. There normally aren't a lot of earthquakes here, but there was a quite big earthquake that destroyed a lot of property, and that was something like 6.0 on the moment magnitude scale. This was back in 1875 or so, and geologists have since determined that there are some ancient faults from a rift zone that isn't really active anymore, but that something possibly very far off movement of a plate caused movement along these dead faults, and that caused a big earthquake. So sometimes intraplate earthquakes can be caused as a result of movement along dead faults. Oops. So any questions before I get a little bit into just what the lab is today? What sort of lab questions you'll be looking at? So lab questions today will be related to movement along faults. So figuring out which one is the hanging and which one is the footwall, and whether the hanging wall is moving up or down, as well as what type of fault you have. Do we have a strike slip fault where we have sideways movement, or do we have a normal fault or reverse fault where we have up or down movement? There'll be some questions about earthquake waves. The question that you are uploading your answer to under the submission window is one where you are locating earthquakes, because we locate earthquakes by measuring when the waves arrive. And we can't usually simply use one location. We have to use 3 separate locations around the earthquake center to triangulate and figure out where it is. And then there will be a couple of questions about how often earthquakes occur, using some data that's provided in the lab to figure out when a large eruption is likely, or excuse me, when a large earthquake is likely at a given fault. And this is due next week, April 26th at 11:59 p.m. This is a bit of a long lab. Feel free to take the time you need on it. Or it's a little bit more involved than some of the previous labs, I'd say. And again, this will be the last lab you do. So any questions before I close the presentation? Okay then, so go ahead and take a look at the Canvas site. The resources you need are all linked within the Canvas page, and I will be around to answer questions.